This is a thrust meter from an Apollo Lunar Module. It has two needles, with the left needle showing the current level of thrust being produced by the descent engine, and the right needle showing the currently commanded throttle percentage. This particular meter is basically brand new. It has its little quality control tag here that says, "Above meter has been inspected per such and found to be acceptable," dated September 25th, 1969. It even came with a little plastic protective cover for the display, stating that we are to be very careful when handling it so as not to damage the anti-reflective coating. Overall, it's in super great shape. There's basically nothing wrong with it. We can take a look at the back here, which has the part tag. It is a servometric indicator, which is a little bit different than your usual Darson-Vahl meter. It actually has a feedback loop from the needles to do closed-loop control using servos of the position of the needles, which makes them much more responsive and much faster to move. It also has the interesting side effect of when there's no power applied to the meter to drive those servos, the needles just sort of stay where they are, which is why they're kind of hanging out in the middle here. Also on the back, we have the connector for it, which has a glass header with feed-through contacts. These are all solder cups, and no indication of pin numbers aside from this little brown circle around this pin, which we can assume to be pin number 1. But to really get all the pin numbers, you either need to do some proper reverse engineering or guesswork, or get your hands on the specification control drawing, which does still exist at the National Archives. And so I got a copy of it, and I'm going to use it to turn this thing on and see to what extent it still works. The SCD has some really nice drawings in it, including, importantly for us, a diagram showing the pin numbers. It also has a pinout table showing the pin assignments for all of the various revisions of the meter. I have the last revision, -16. As you can probably see, this meter changed a lot over time. Only the last 3 revisions have pins 13 and 14, which, despite their names, are not actually power inputs, although they are shorted to the power inputs internally. Instead, they are a workaround for the problem that I noted earlier, where the needles, when the meter loses power, will just kind of hang out at their last reported position. You can imagine for something like a thrust meter that this is super undesirable behavior if you are in the middle of a burn and your meter loses power and it just starts lying to you about what the actual thrust level is. The fix for this was to route power back out of the meter to open a relay to turn off a light, which is mounted just above the meter on the panel. When the meter loses power, the relay closes again, and the light turns on, and you know that your meter is now off. But even outside of these two interesting pins, there's a surprising amount going on this connector. For example, we have 3 analog inputs for a meter with 2 needles. Also, what's up with these bias pins? Well, like I said, this meter is wired in a really interesting way. Let's start by looking at the left needle, the actual thrust needle, which is pretty straightforward. It's directly driven by a 200 psi pressure transducer that puts out 0 to 5 volts and measures the chamber pressure of the descent engine. And that's basically all there is to it. The right needle is where things start to get weird, and it all stems from the fact that there are 2 sources of throttle control in the lunar module. The TTCA, or Thrust and Translation Controller Assembly, which gives manual throttle control, and the Apollo Guidance Computer, which senses vehicle accelerations to do closed-loop, automatic throttle control. Accordingly, there is a switch called Engine Thrust Control that can be switched between auto and man to select the control mode. The manual position does basically what you would expect and makes it so that the engine throttle only responds to the TTCA, although there is one little catch. The engine can't be throttled below 10%, and so to prevent the possibility of a manual command of less than 10%, they actually made the minimum position of the TTCA handle 10%. And so the TTCA is always commanding at least 10% to the engine. Possibly for this reason, the auto position of the switch is not just the automatic command from the AGC. It actually sums the manual command with the AGC's automatic command. Interestingly, this summing happens inside the throttle actuator in the engine itself. And if you look at this diagram closely, you might notice something. That sum is used to control the throttle valves, but it never leaves the engine, meaning it does not go to telemetry, and it doesn't go to our poor meter. So how does the meter know what to display? You might think that maybe the automatic command and manual command are summed up somewhere else. Maybe before the meter, maybe inside the meter. But no, this is not what happens. Instead, a relay is set up to track the position of the thrust control switch and switch signals into and out of the meter. When the switch is in manual, the manual throttle command is connected to the manual input pin on the meter. And when the switch is in auto, the auto command is connected to the auto input pin. Why two different pins? For whatever reason, the two had very slightly different scale factors, and so for precision, you want to make sure you're running the right signal into the right pin. Now, everything will work as expected when the switch is in manual. The right needle will exactly reflect the manual command coming out of the TTCA. But things get weird when you go to auto, because the meter will only be getting the auto contribution to the throttle command, even though the throttle is responding to the sum of the auto command and the manual command. And this is where those bias pins come in. You see, it's standard procedure to leave the TTCA in its minimum position, commanding 10%, whenever an automatic burn is being performed. And so the meter basically makes this assumption. It internally regulates a reference voltage equivalent to 10% on the right needle and exposes it on one of the three bias pins. The relay then switches this bias to a bias input pin depending on the state of the thrust control switch. So if the switch goes to auto, that 10% bias is routed back into the meter and summed with the auto input. Problem solved. At least, as long as your throttle lever is actually in the minimum position. If it's not, things get weird. Imagine that you're performing an automatic burn and the AGC is providing closed-loop throttle control. That basically means that it is controlling the left needle to a particular value. If you were to start pushing the TTCA handle forward, the manual command of the throttle will increase, and so the AGC has to decrease its command in order to compensate. But because the meter can only see the AGC's automatic command, the right needle will actually go down as you push the TTCA handle forward, even though the actual total throttle command is staying the same. It'll continue decreasing until it hits 10%, at which point it's only showing the bias, and the AGC is commanding 0. Believe it or not, doing exactly that is the official way to switch from automatic control to manual control during a burn. This is perhaps another reason why they kept the automatic and manual inputs to the meter separate, so you could do this smooth handoff as long as you don't think too much about what that right needle is saying. Anyways, that was a weirdly deep rabbit hole for 1 meter, but let's go apply what we've learned and turn this thing on. Since this thing is in such good condition, I really don't want to solder to those solder cups. So instead, I measured the diameter, and it's about 0.062 inches. And I went shopping on DigiKey and managed to find some female crimp contacts that exactly expect a 0.062 male pin diameter to mate with, and they fit perfectly. So, using those, I built a harness that has an integrated thrust control switch to go between manual and auto, and convenient inputs for power and signals. I decided to just leave loose wires for actually mating with the back of the meter. I might SLA print a connector for it later, but for now, just the heat shrink over the contact should work well enough for our purposes. All right, let's turn it on. 28 volts. So the meter draws 30 milliamps or so when it's running. I have it in manual right now, and so the left needle is showing 0 because I'm feeding in 0 volts, and the right needle is showing less than 0 because it's not sure what to do because I'm not giving it the expected minimum 10% input. But we can switch between auto and manual and see that bias being applied when I go to auto. So there's the 10% bias, but we'll stay in manual for now. Let's get the left needle moving. So the left needle is driven by a 200 psi 5 volt pressure transducer. And according to the Apollo Operations Handbook, the nominal chamber pressure is 103.4 psi at a nominal throttle level of 94%. And so if we do the math, we should hit 100% on the left needle at 2.75 volts. So let's see how well this thing is still calibrated. 2.6, 2.7, and there's 2.75. That looks pretty good to me, honestly. That's right about 100%. So left side seems to still be nicely calibrated after, 50, 60 years of sitting around. And then the right needle, we're in manual right now, so I believe that the minimum output from the TTCA corresponding to 10% should be 0.89 volts. So let's try that first. So there's 0.8, 0.89, and that does look like it's about 10%. And then 100% is 4.658 volts. So let's go there. Get ourselves up to 4.658. All right, so there is our manual 100%. And again, it's bang on, basically 100%, which is pretty cool after so many years of sitting around. So let me rewire for the automatic input now. All right, we're wired for auto. Just as a demonstration, I suppose, I will show that applying voltage now doesn't do anything because we're still in the manual switch setting. So go back to 0 volts, switch to auto, we get our 10% bias, and now as I apply voltage, our needle starts to go up. On auto, 100% is 4.583 volts. So 4.583, and once again, bang on. So this thing is basically still perfectly calibrated after 50-something years, which is very cool, but I guess really not unexpected for Apollo hardware, given everything that we've seen so far. One interesting thing that I've noticed is that when one needle makes a big move, like we are doing here with our right needle, switching between manual and auto, the other needle has like a glitch, and then it controls back to the right position. I'm not exactly sure where this glitch is coming into the system. I assume that this has to be coming from inside the meter, and it's not like a current limit situation going on, but kind of interesting real-world behavior that you might not necessarily expect. Alright, now I've got my function generator set up to provide the inputs so we can see some nice clean sweeps. Here we go, both alternating between 100% and 0% on the left and 10% on the right, or roughly speaking at least. I can give a phase offset to that to make it look more interesting. Yeah, let's get up to 90 degrees phase there. Yeah, there we go. How cool is that? Alright, so the last thing that I haven't talked about is lighting. This thing actually has full electroluminescent lighting. Everything that is white that you can see on the front panel is electroluminescent. So let me get that wired up, and then we'll turn off the lights and see how that looks. Alright, lights are off. So let's get the meter powered on. There's power to the meter. I'm sure you heard it. But now, it takes 0 to 75 volts AC at 400 hertz. So I have an AC power supply up here, and I'm going to start cranking up the AC voltage to it. And there it is. There. So that's max brightness. Usually, there is a lighting override switch that you can throw that applies 115 volts directly to the lighting instead of 75. But 75 volts provided plenty of light in the dark LEM, as you can tell. And so the normal dimmer circuit only went 0 to 75 volts. So I'll turn it down, and then I will do that again. Nice and zoomed in on the meter so you can see it come on. While I was at it, I took the opportunity to take a rough optical spectrum of the EL. It doesn't put out a lot of light, and so the readings are a little bit intermittent and inconsistent, but this, I think, was the best data set I was able to capture, and I was able to reproduce these numbers a couple times, so I think they're at least somewhat accurate. But the overall idea is that there are two peaks at roughly 480 and 590 that sum together to produce a display that's pretty white, with a color temperature certainly north of 6,000 Kelvin and probably less than 6,500. One last little thing that I've noticed is that the meter, and I guess servometric meters in general, don't necessarily hold their needle positions strongly through vibration. So if I give it a good shake, you'll see that the needles have moved and now they're stuck at a new position. This is interesting from a launch point of view because it means theoretically, if you launch with unpowered meters, like would happen in the lunar module, when you first enter the lunar module and look at the meters, maybe the vibration from launch might have moved the needles to random, weird, nonsense positions that they'll continue to read until you apply power to those meters. So we looked into it a bit. This is a picture from Apollo 15, taken as part of Lunar Module closeout during the countdown. And this is a picture taken during LEM activation after launch. Taken, of course, because of the broken glass on the tape meters. But comparing the two images, it doesn't seem like the needles have moved very much, so I don't know. By the way, here's an interesting question. Why is that thrust meter registering thrust on the pad? I'll give you a second. It's because it was calibrated for use in a vacuum, but sitting on the pad, the engine chamber has about 1 atmosphere in it, and if you do the math, that corresponds to just over 13% of the max chamber pressure. And that's exactly what the meter is showing, which is kind of cool. Alright, that's all I've got. Thanks for watching, and I will see you guys next time.